In 12.3, we're going to continue on with our polar equations, but now we're going to apply our calculus, so we're going to figure out derivatives and integrals. We're going to derive the formula for the derivative of a polar function. So just recall that when you find the derivative of y with respect to x, that's going to be the rate of change of vertical movement and horizontal movement, right? Because the y is vertical up, down. The horizontal, the x, is left, right movement. Polar coordinates aren't made that way. So since they don't correspond to vertical and horizontal coordinates, we can't just simply find the derivative r prime. Okay? We need to first translate to parametric form and use theta as the parameter. So we're going to go ahead and derive the formula for the derivative of a polar equation. But first note that if we do have a polar equation r, it is a function of theta. So going back to our x value, which is r cosine theta, we can now write the x value as r is going to be f of theta, cosine of theta. And since y is equal to r sine theta, we can write our y value as a function of theta times sine of theta. Going back to our parametric, when we find the derivative, we simply take the derivative of y. In this case, y is a function of theta, so it'd be dy d theta, the derivative of y over the derivative of x, which again is a function of theta, so it's dx d theta. In other words, this would be y prime of theta over x prime of theta. Notice that when we compute that, y is a product of two functions of theta, so what we have to do is we have to use the product rule, which means we take the derivative of f, we keep sine, plus keep our function f, the derivative of sine would be cosine, over, we'll take the derivative of our x, which again involves the product rule, so it's kind of the same thing. The derivative of f, cosine stays the same, plus f stays the same. The derivative of cosine is negative sine. So if I were to factor out the negative in front of sine and change it to a minus f of theta times sine theta, then what we get is what's inside the table here, which is our derivative of a polar function. So it's nice to derive it, because then it's easier to memorize if you ever have to memorize, but you do have notes on the exam, so no worries there. So something to note is that as long as the denominator is not 0, if the function is equal to 0, meaning it's going to pass through the origin, and the derivative is not 0, then our tangent line is just going to be theta equal to whatever this theta sub 0 or theta naught value is. So this is the formula for a derivative at some point theta naught. Typically, if we write tangent lines in polar forms, we're just looking at tangent lines that pass through the origin, because that's an easy line to write in polar form. Otherwise, you can always find a tangent line on any polar curve, but if it's not a tangent line that passes through the origin, we usually will write it in terms of x and y coordinates. Let's look at example 1. It says to find the slope of the line tangent to the polar curve at the given point. So that's what I'm going to do first. Slope of a tangent line means I have to find the derivative. Now the second part of this example says if the curve intersects the origin, so that has nothing to do with the point that I was given. If the curve intersects the origin, Find the equation of the tangent line in polar coordinates. So there's two things going on here. So first I'm going to find the slope of the tangent line at the given point. So the given point is 2 comma 5 pi over 6. So to find the slope of the tangent line, I have to compute the derivative of my function r, which, would give me dy over dx equal to, remember it's the derivative of 4 sine theta, which would be 4 cosine of theta, plus, not plus, times the 4 sine theta. So that would be times, and we keep our sine theta. Plus, the function stays the same, so 4 sine theta times cosine theta. All over, derivative is 4 cosine theta times cosine minus 4 sine theta times sine of theta. Let's see if we can make this look a little bit nicer. So in the top, well, you know, it looks like maybe I can go ahead and factor out a 4 top and bottom and cancel it. Let's see, so I have cosine sine plus cosine sine, which would give me a 2 sine cosine in the numerator. In the denominator, it's cosine squared minus sine squared. Now if you want to write that in a different way, because cosine squared minus sine squared is actually cosine of 2 theta, so you could use a trig identity there. But I'm just going to leave it that way, because I'm supposed to find the slope of the tangent line at the given point. I'm going to compute that now. So the derivative is going to be evaluated for the theta value, because we're putting theta into our derivative, and the theta value is 5 pi over 6. Notice that that's going to give me 2 times sine of 5 pi over 6 is going to be 1/2 times cosine of 5 pi over 6, which should be negative square root 3 over 2, over cosine of theta is square root 3 over 2, negative square root 3 over 2. But I'm going to be squaring that, so it's going to turn into 3/4 minus sine of theta is 1/2 squared is going to be 1/4. Clean this up a little bit. I have negative square root 3 over 2 over 1/2. Looks like it's going to be a negative square root of 3. So we answered the first part of the question. It just said to find the slope of the tangent line at the given point. And this would be the slope of our tangent line. Now the rest of this, the second sentence says, if the curve intersects the origin, find the equation of the tangent line in polar coordinates. When you look at the equation r equal 4 sine theta, and again, you could put this in your graphing utility or your calculator, notice that when theta is 0, r is equal to 0. So that passes through the point 0, 0, which is the pole. But it's not just when theta is equal to 0. When theta is equal to pi, r is equal to 0. So as long as r is equal to 0, then we're passing through the pole. Notice that there's infinitely many theta values that will give us an r value of 0. So we just have to pick one. So I'm just going to pick the first theta value I got, which is theta equal to 0. And then in polar form, this is a tangent line of theta equal to 0. Okay. I could have used theta is equal to pi. I could have used theta is equal to 2 pi or negative pi. Doesn't matter. They'll all give me the same line, same tangent line. Okay, so this happens when theta is equal to 0. But it also happens for other theta values. All right, in example 2, we're given an equation r. We're given theta values from 0 to 2 pi. And in this example, we're supposed to find the points at which our polar curve has a horizontal or vertical tangent line. So remember, if there is a horizontal tangent line, that means we have a slope of 0. If we have a vertical tangent line, that means we have an undefined slope. What I'm going to do is I'm going to compute the derivative, and then I'm going to look where we're going to get a fraction, right? And fractions are 0 where the numerator is 0, but the denominator is not 0. So first I'm going to compute the derivative. So it's going to be the derivative of r, which is going to be negative cosine theta. Oops. Times sine theta plus, function stays the same, 1 minus sine theta times cosine of theta. This is all over negative cosine theta times cosine of theta minus 1 minus sine theta times sine of theta. You could probably write that in a nicer way. Maybe in the numerator I can distribute that cosine, and yet maybe something nicer. Okay, so it looks like in the numerator I'm going to get cosine of theta minus 2 sine cosine. And then that 2 sine cosine, if you want to use a trig identity to write that as sine of 2 theta, you can. In the numerator, it looks like I'm going to have a negative cosine squared theta plus sine squared minus sine. Again, you could play around with it some more. I just wanted to clean it up a little bit, get rid of those parentheses for now. And look at what it means to have a horizontal tangent line. So there's a horizontal tangent line if the slope is equal to 0. The slope, or a derivative, is a fraction. So that will occur when the numerator, cosine of theta minus 2 sine theta, cosine theta, when that's equal to 0. So algebraically, I think what I'm going to do is, since I do have an equation set equal to 0, I'm going to go ahead and factor out the cosine, and I'll have 1 minus 2 sine of theta equal to 0. So this is just solving a trig equation. Okay, so I have factored equal to 0, then that must be true that cosine of theta is equal to 0, and 1 minus 2 sine of theta is equal to 0. Remember, my theta values are just from 0 to 2 pi. So if I look at this first equation here, cosine of theta equal to 0, I can see that my theta value has to be pi over 2 or 3 pi over 2. Those are the only choices in the interval that I was given. The second equation, if I were to solve for sine of theta, I would minus 1 divide by negative 2 to get sine of theta equal to a positive 1/2. And then solving this equation for theta, I have theta is equal to pi over 6 and 5 pi over 6. And those are the only two theta values between 0 and 2 pi that will work. Okay. So remember, I'm looking at where my derivative is equal to 0. So I just set my numerator equal to 0, but I do have to be careful, because if any of these theta values also makes the denominator equal to 0, then I have a 0 over 0, which is not where a horizontal tangent line is. Remember, that's indeterminate form. It turns out if I put pi over 2 into the denominator of my derivative, I get 0. Okay, so that is not where a horizontal tangent line occurs. For the other three theta values, they will correspond to points on my graph. So at 3 pi over 2, now I'm putting that back into my function because I'm trying to find a point on my function r at which we have a horizontal tangent line. So if you put 3 pi over 2 back into your r function, you'll get the point 2 comma 3 pi over 2. So that's where there's a horizontal tangent line. And then if we put in pi over 6, we get 1/2 pi over 6. That's another point on our function r where there's a horizontal tangent line. And you can always graph the function r and just look at it and imagine where your horizontal tangent lines would be. And 5 pi over 6 will give us an r value of 1/2. So 1/2 comma 5 pi over 6. These are the 3 points at which we have horizontal tangent lines. To find vertical tangent lines, what we do is we set our denominator equal to 0. So that point theta is equal to pi over 2. That could possibly be where there's a vertical tangent line. So remember, we're setting the denominator, which is negative cosine squared theta plus sine squared theta minus sine of theta. We're looking at where the denominator is equal to 0 or where it's undefined. Now that negative cosine squared theta, cosine squared is 1 minus sine squared. So this is negative in parentheses 1 minus sine squared. What I'm doing here is I'm going to write this expression with only signs because that seems to me to be the easiest way to solve this trig equation. And then getting rid of the parentheses, combining some like terms, I should end up with 2 sine squared theta minus sine theta minus 1 equal to 0. That looks like something that I can factor into 2 sine theta plus 1 sine of theta minus 1. and then setting each one of these factors equal to 0, and solving for my theta values from 0 to 2 pi. Let's see what we get. All right, so minus 1 divided by 2, and I get sine of theta is equal to negative 1/2, and sine of theta is equal to 1. In this first equation, sine is going to be a negative 1/2 at 7 pi over 6 and 11 pi over 6. So that's when theta is equal to 7 pi over 6 and 11 pi over 6. In our second equation, sine is equal to 1 when theta is equal to pi over 2. Notice that pi over 2 came back. So that's where the denominator is 0. And again, if you graph r equal to 1 minus sine theta, you'll see that there will be vertical tangent lines when theta is 7 pi over 6, 11 pi over 6, and also at pi over 2. Okay. Putting those values into our r function for theta, we have the point 3/2, comma, 7 pi over 6, three halves, 11 pi over 6. And we also have a vertical tangent line at 0 pi over 2. All right. Let's move on to some more calculus concepts. We talked about derivatives. We looked at how you compute the derivative, finding horizontal, where we have horizontal and vertical tangent lines. The next thing we're going to look at is we're going to look at integrals. So unlike our usual XY coordinate system, where we're adding up the areas of very skinny rectangles when we compute our integral, you got to think about this. Remember that polar coordinates are angular, they're circular movements. So we're really not adding up areas of rectangles when we compute the area in polar. What we're adding up is we're adding up the area of sectors. Okay? So an area of a sector again, if you remember this from trig, is 1/2 r squared times theta, which is where this formula comes from. We have our 1/2, and then this f of theta squared minus g of theta squared. That's our r squared. If we have two functions, it's always the larger squared minus the smaller squared. So that's just how we find areas when we compute integrals, right? Larger minus smaller. So this would represent our r squared. And then our d theta is our theta value, just a very, very small theta value. Example 3, we're supposed to find the area inside the region of r equal to 2 plus cosine of theta. So I strongly recommend that you graph the region first. When I graph this region, it's going to be, oh gosh, I'm the worst at hand drawing graphs. I guess that's not too bad. It's going to look something like this. It's going to start when theta is equal to 0, and then the graph goes all the way around and comes back here at theta equal to 2 pi. So that's when we have our complete graph. And that's something you need to know. You need to know your limits of integration. Well, notice that there's this symmetry here. And this you can often do with polar graphs. You don't have to compute the whole integral from 0 to 2 pi. You can always just go from 0 to pi, and because there's this really nice symmetry, you could just times that area by 2, which is what I'm going to do, and there's a reason why I'm going to do this. Because we have that 1/2 in the integral, and the 2 and the 1/2 will cancel if I go from 0 to pi and just times that area by 2. So this is 2 plus cosine squared quantity squared d theta. And again, notice the reason I did that was so that I could cancel this 1/2 and this 2. Sometimes you can't use symmetry, but in this case I can. Okay. Again, you don't have to. You can just go from 0 to 2 pi and not worry about it. I'm going to go ahead and multiply out 2 plus cosine theta. Remember, you're foiling that. So it actually ends up to be 4 plus 4 cosine of theta plus cosine squared theta. And I'm doing this just because I don't know how to integrate 2 plus cosine theta quantity squared. So I know how to integrate 4 and 4 cosine, but I don't know how to integrate this cosine squared. So I'm going to use a trig identity that says cosine squared is equal to 1 plus cosine of 2 theta over 2, which is just equal to 1/2 plus 1/2 cosine of theta. And then I think I can simplify this even further, this integrand, because I have this 1/2 that I could add to the 4 if I wish. Or you could leave it the way it is. Oops, and I forgot to write on the other side that it's 2 theta. Sorry, this should be a 2 theta. All right, that I know how to integrate. But I think I will clean it up a little bit. My handwriting's awful today. So 4 plus 1/2 will give me 9/2. Plus 4 cosine of theta plus 1/2 cosine of 2 theta. And now the antiderivative will be 9/2 times theta plus 4 cosine of theta. Oh, sorry. 4 sine of theta. Sorry about that. Plus the antiderivative of cosine of 2 theta is sine of 2 theta times 1/2. But I've already got that other 1/2 in front, so it'll turn into 1/4 sine of 2 theta. And we'll evaluate from 0 to pi. When I put in pi for theta, I get 9/2 pi. Putting in pi into sine just gives me 0. Okay. And then when I do minus 0, the whole thing's 0. So we actually just end up with 9/2 pi, or 9 pi over 2. Let's do another integral. we're going to find the area of the region of one petal of this rose. R is equal to cosine of 3 theta. So again, we want to go ahead and graph this first. And that's because my limits of integration were not given to me. So if I graph this, oh, and this is where I get to draw by hand, we get this 3, well, that's not that bad, 3 leaf or 3 petal rose. And I'm supposed to find the area of that whole region. But again, I don't want to. I want to use symmetry. So if I just look at the upper part, and you don't have to do this, the upper part of that first petal or leaf, it will be bounded by, oops, I don't want a thick line, by theta equal to 0. And here, this is theta equal to pi over 6. So that one piece that I'm looking at, this piece here, I've got 1, 2, 3, 4, 5, how many am I gonna? Oh, so I'm just trying to find the area of the region of one petal. Oh, okay, well then I can do what I did before. I'm just gonna take that one piece and I'm gonna multiply it by 2. So my area is gonna be 2 times the integral from 0 to pi over 6 of 1/2 of cosine 3 theta squared d theta. Okay, so that's not so bad. If I had to find the area of all 3 petals, then I could just, instead of multiplying that by 2, I can multiply it by 6. And nice, these guys will cancel. And I have another problem. Because this is going to be cosine squared of 3 theta d theta, and I don't know how to find the antiderivative for cosine squared. So I'm going to go back to my trig identity. Just keep in mind that the argument here is 3 theta. It's not just theta. So when we simplify this, or write it in a different way, it's going to be 1 plus cosine of 6 theta, right? You're just doubling the argument over 2. In other words, it's going to be 1/2 plus 1/2 cosine of 6 times theta d theta. I don't feel like working with all those halves. I think I'm going to, and now you don't have to do this, I think I'm going to factor out the 1/2. I don't know if it's going to make things nicer or not, but we'll find out. So factoring that out, I get 1 plus cosine of 6 theta. It looks nicer. Which gives me theta plus 1/6 sine of 6 theta. And then I'm going to be evaluating that 0 to pi over 6. Again, you didn't have to do that. I have a 1/2. Let's see, if theta is pi over 6, let's see, sine of 6 times pi over 6 is sine of pi, which is just 0. And then minus 0. Okay. It looks like it's just pi over 12. And then let's look at one last example. We're going to look at an example where we actually have two polar equations. So we want to find the area of the region outside of the circle r equal to 1/2 and inside the circle r equal to cosine of theta. Again, really helpful if you graph this. Let's see. The circle r is equal to 1/2. That's just a circle at the origin with a radius of 1/2. And r cosine of theta, I'm going to do this in a different color. So r cosine of theta is a circle here. So it's going to be the region outside of the green circle, but inside of the red circle. We're looking at this region. All right, so this is where in the formula where it had an f of theta squared minus a g of theta squared. In this case, we have to determine the outer and the inner function as we're integrating. So to find that area, again, I notice that there's a symmetry. So maybe I can just look at integrating from, I always forget to change it, from theta equal to 0 to whatever this point is here, and look at this theta value. I need to determine what that value is. To find that, I can do this algebraically. All I have to do is set cosine of theta, set the two equations equal to each other. So let cosine of theta equal to 1/2. And then I could see that theta would have to be pi over 3. So this is theta equal to pi over 3. So if I just integrate from theta is equal to 0 to theta is equal to pi over 2. I said pi over 3 and I wrote pi over 2. Pi over 3. Then I could just multiply that region by 2. Our integral is now 2 times the integral from 0 to pi over 3 of 1/2. It's going to be the larger minus the smaller. So looking at this graph, I see this red curve is the larger. The green curve is the smaller. Okay? Which would mean it's cosine squared minus 1/2 squared. So cosine squared minus 1/2 squared, which would be 1/4. So that would be the integral that I would set up. And again, I'm going to cancel the 2 and the 1/2 with a reminder that sometimes it doesn't work out nicely like that. But if it does, take advantage of it. And we're going to integrate from 0 to pi over 3 of cosine squared theta minus 1/4 d theta. And I'm going to replace the cosine squared with 1/2 plus 1/2 cosine of 2 theta minus 1/4. And then the 1/2 minus 1/4 will just be a positive 1/4. Again, you don't have to combine, but it turns out nicer. At this point here, I can clear fractions if I wish, but I think I'm just going to leave them the way they are. This is going to be a 1/4 theta. Antiderivative cosine is sine, but it's sine of 2 theta over 2, which would give me a plus 1/4 sine 2 theta. I evaluate it from 0 to pi over 3. Putting in pi over 3 for theta, I have pi over 12. Plus 2 pi over 3 for sine. And that would be square root 3 over 2 times 1/4. And then minus 0, minus 0. I usually don't write that. Okay, so that's 3 over 8. So pi over 12 plus square root 3 over 8. And you could combine this by finding common denominators, but I'm just going to stop right here. And that's it for this section.